The physicist Freeman Dyson puts the work of Cantor and Peano in context.
A great revolution of ideas separates the classical mathematics of the 19th century from the modern mathematics of the 20th. Classical mathematics had its roots in the regular geometric structures of Euclid and the continuously evolving dynamics of Newton. Modern mathematics began with Cantor's set theory and Peano's space-filling curve. Historically, the revolution was forced by the discovery of mathematical structures that did not fit the patterns of Euclid and Newton. These new structures were regarded as pathological, as a gallery of monsters, kin to the Cubist painting and atonal music that were upsetting established standards of taste in the arts at about the same time. The mathematicians who created the monsters regarded them as important in showing that the world of pure mathematics contains a richness of possibilities going far beyond the simple structures that they saw in nature. 20th century mathematics flowered in the belief that it had transcended completely the limitations imposed by its natural origins.
But Dyson concludes that there is an ironic twist to the story.
Now, as Mandelbrot points out, nature has played a joke on the mathematicians. The 19th century mathematicians may have been lacking in imagination, but nature was not. The same pathological structures that the mathematicians invented to break loose from 19th century naturalism turn out to be inherent in familiar objects all around us.
Mandelbrot states this conclusion as a manifesto.
There is a fractal face to the geometry of nature.
One of the first natural objects to attract Mandelbrot's attention was the coastline of Britain. He asked how long it is. Actually, the question had been posed by the British scientist Lewis Fry Richardson before his death in 1955. But Richardson had been ahead of his time. Mandelbrot was inspired by Richardson's work to take up a silly-sounding question and pursue its implications.
Consider a stretch of coastline. It is evident that its length is at least equal to the distance measured along a straight line between its beginning and its end. However, the typical coastline is irregular and winding, and there is no question it is much longer than the straight line between its endpoints. There are various ways of evaluating its length more accurately. In each case, the result is most peculiar. Coastline length turns out to be an elusive notion that slips between the fingers of one who wants to grasp it. All measurement methods ultimately lead to the conclusion that the typical coastline's length is very large, and so ill-determined that it is best considered infinite. For example, as you measure the coast of a country with ever-increasing precision, its length becomes greater because you have to take into account ever smaller irregularities along the length. Hence, if one wishes to compare different coastlines from the viewpoint of their sizes, length is an inadequate concept.
Of course, Mandelbrot could be speaking of any objects with irregular features. The coastline is just one example. Mandelbrot refers to a coastline problem described by Richardson.
The length of the common frontiers between Spain and Portugal, or between Belgium and Netherlands, as reported in those neighbors' encyclopedias, differ by 20%. The discrepancy must, in part at least, result from different choices of scale of measurement, and one should not be surprised that a small country like Portugal measures its borders more accurately than its big neighbor.
Mandelbrot then concludes,
if coastlines are ever to become an object of scientific inquiry, the uncertainty concerning their length cannot be wished away. In one manner or another, the concept of geographical length is not as inoffensive as it seems. It is not entirely objective. The observer inevitably intervenes in its definition.
how then can coastlines or other objects with complex shapes be understood?
Within the range of scales of interest to the geographer, coastlines can be modeled by fractal curves. Coastlines are fractal patterns.
Fractal patterns, strictly speaking, are defined by their dimension. In the Euclidean tradition, we think of objects as having dimensions given by whole numbers. A line has one dimension, a square has two dimensions, and a cube has three dimensions. But fractal objects have fractional dimensions. A coastline, for example, may be sufficiently convoluted to have a dimension of 1.42. It's more than just a line, but not yet a two-dimensional surface. Indeed, this concept of fractional dimensions is the source of the name of this new math, fractals. Fractals are mathematical objects that can be fully understood only by using the austere, highly abstract, theorem-proving techniques of modern mathematics. But at the same time, the study of fractals seems to be an essentially visual enterprise. Indeed, it's difficult to talk about fractals without also showing them. Most writing on the subject is heavily illustrated, and photographs of computer-generated fractals have been shown internationally as art exhibits. The visual qualities and the aesthetics of fractals have certainly been part of their appeal, attracting the attention of both scientists and the general public. This heavy reliance on visual displays has led some mathematicians to charge that fractals are not really serious mathematics, but the science writer Robert Poole says otherwise.
To the charge that fractals are little more than pretty pictures, Mandelbrot responds that studying fractals helps develop an intuition for certain mathematical problems that cannot be developed in any other way, and that this insight leads to both new conjectures and new approaches to solving some profound mathematical theorems. His work, and the work of other fractal geometers, is in the tradition of geometrically minded mathematicians of the 19th century, who drew pictures to gain insights. That approach stalled when the mathematics got too complicated for pencil and paper, but computers make it feasible once again.
Mandelbrot is more pithy.
In the appropriate minds, pretty pictures lead to pretty problems and to entirely new fields.
He then elaborates on how fractals have energized mathematical research, especially research involving iteration, in which calculations are continually repeated in order to study the sequence of results that is produced.
Ordinarily, mathematical conjectures originate in previously known theorems. In recent decades, there was no input whatsoever from physics or from graphics, which meant that some areas of pure mathematics, such as the theory of iteration of functions, simply ran out of steam. Fractal pictures done at the computer have revived the theory of iteration. Being able to play with pictures interactively has provided a deep well for mathematical discoveries. Examining those pictures has led to many conjectures that were simple to state, but hard to prove. Studying them has produced a host of interesting side results.
The Dutch mathematical biologist Aristide Lindenmayer led a group in the 1970s and 1980s whose work clearly illustrates why the visual, graphical aspect of fractals is important in scientific applications. Lindenmayer was a pioneer in trying to understand the logic rather than the chemistry of how plants develop their characteristic physical shape in a biological process known as morphogenesis. Lindenmayer was the first to ask whether morphogenesis is best understood as the result of repeatedly applying a simple set of rules, or whether it's the manifestation of a universal law. In Lindenmayer's study of morphogenesis, a computer is the laboratory. Hypothetical rules are developed to describe the growth of a plant, and then the computer grows it. The output is always graphical. An image of the growing plant appears on the monitor. Lindenmayer and his collaborator, Przemysław Prosienkiewicz, explain why this visual aspect is so important.